All right, so today I'll talk, there will be 3 parts. The QC basics, which is kind of include also the empire problem, which is the second one. And then the third one is the Penrose Tiling, the ribbon dynamics. So it's kind of 3 topics for today. Tomorrow will be like a lot more. I have to think about how to organize that. So the QC basics, because this is the outline what I'm gonna talk about, because our group is focused on using quasicrystal mass to model physics. So the most fundamental thing is to know what is quasicrystal, and then I will talk about how to generate the quasicrystal mathematically, not in the lab, so don't ask me the question like that. Although Russ can answer the question. Yeah, so I will cover the 3 ways of generating the quasicrystal mathematically using substitution rules, the dual grid method, and the cut and project from high dimensional crystal. And then I will talk a little bit about the properties of the quasicrystal. The properties which include, I only cover like 2 aspects. One aspect is the non-locality, and the second one is the phason dynamics. Actually, I think these 2 actually would be moved to as a individual subject later, different presentations, right? So what is quasicrystal? So far there is still like not agreed upon definition for quasicrystal. There's still, even in the quasicrystal conference.
Sorry to interrupt. Can you be a little closer to the screen, possibly?
Oh, okay.
Thank you. Let's start over with
just
what is quasicrystal.
like I don't block anyone.
Just not too far, so I don't.
Okay.
Thanks.
Okay. So yeah, so even in the quasicrystal conference, they're still arguing about the definition for quasicrystal. So some think the quasicrystal is, like belongs to the crystal family. Some think it's not. But anyway, so I found 2 definitions, and then the first one, I got this is mostly from Wikipedia. It's kind of like a more or less like people agreed definition. So here it says, actually no, this definition I got from Paul Steinhardt's paper. Okay, so I like the way that his series of paper on quasicrystals. Just want to recommend for you guys. He has a quasicrystal 1 and quasicrystal 2, and the third paper is how to generate quasicrystal with arbitrary symmetry or something like that. So the 3 papers, which is really nice. So the definition that his group gave is an ideal quasicrystal is constructed by the infinite repetition in space of 2 or more distinct structural units called unit cells, that we know, packed in a lattice that has long-range quasi-periodic translational order and long-range orientational order. So some keywords. So there has to be finite number, excuse me, finite number of unit cells, and the unit cells would repeat and pack a space or in a lattice that has long-range quasi-periodic translational order. It does have translational order. It's just like not like in crystal, it's a local translational order, repeating. And this is like if in quasicrystal, if you can find any patch of the quasicrystal you find in the quasicrystal, you can like any patch in the quasicrystal, you can find an identical patch somewhere else in a quasicrystal. So that's also part of the definition. So anyway, so that's one thing. Another thing is it has this long-range orientational order. It has this rotational order. So like 5, like with the kind of like a forbidden the forbidden symmetry, which is a 5-fold symmetry for crystal, usually 5, and there's 8 and 12, etc. Okay, so this is another definition I got from Seneschal's book. It says an n-dimensional quasicrystal is a crystal whose diffraction pattern exhibits symmetry forbidden by the crystallographic restriction for En. So it's like, in two-dimensional space, for example, there is no a crystal with 5-fold symmetry. So like in E2, and so for example, if you have a kind of like a structure or lattice that has a 5-fold symmetry, it's more like, and then its diffraction pattern shows discrete 5-fold symmetry, and based on this definition, that would be a quasicrystal. And then also this one, I guess, I don't know. I think it does include this part, the finite unit cells, because if you can find an infinite number of unit cells, I think in the diffraction pattern it will be more like smeared. You will not find like really sharp, like the peaks. So anyway, so and then the next one I'm gonna say is how to generate a quasicrystal mathematically. So as I said, I'll talk about the substitution rules, I'll talk about dual grid method, and I'll talk about the cut and project method. So substitution rules, I'll give an example here. Take the one-dimensional Fibonacci chain as an example. So the substitution rule for the one-dimensional Fibonacci chain is if you have an L and then you replace it with an LS, and if you have an S, you replace it with L. So it does not matter if you start with an S or L, because if you started with an S, it will change it to an L. So, does not matter where you start.
Can you define LS for those who do not know?
Well, it's two segments in Fibonacci chain. Usually, when we talk about the Fibonacci chain, the L is golden ratio times the S, which they both are segments. In their length has a golden ratio relationship. So L kind of represents long, that's short. So this L is golden ratio times of the short for their lengths. Okay. All right. So then from S to L, and then L become LS, and S become L, and then the L become LS, S become L, L become LS. So you can continue going. So then this way you build up a quasicrystal. I mean, using this rule, of course, it's kind of like with finite steps, you always get a finite quasicrystal. But most of the quasicrystals we're talking, ideally they're infinite, but usually when we talk about it, it's okay to consider a finite patch of quasicrystal. So that's a substitution rule. Is that clear to everyone? It's pretty simple. Okay, the dual grid method. I'm going to use the Penrose Tiling example. So for Penrose Tiling, the dual grid is called pentagrid because it has 5-fold symmetry. And then penta, it's from pentagon, the word. So what is a pentagrid? So firstly, you set up like 5 directions. So for each direction, you build this a grade that is perpendicular to this direction, perpendicular to that direction. You build a set of parallel lines. So you have 5 of them. It's blue, purple, green, and the yellow. So anyway, so then after you build out this grade, it is called this grade is called pentagrid. And then you can see that, for example, this one, you can shift this grade, right? You can shift it around. Like you can move this whole purple one, for example, up and down. So there are various ways like you can actually compose these 5 sets of parallel lines together. But depending on how you do it, so there is this this shift vector. Okay, so the shift vector is actually the distance between this and the closest line in this line set. For example, in this parallel line set. So consider that is gamma 1, and this is gamma 2, gamma 3, and then it's gamma 1, 2, 3, and then 4 and 5. Anyway, so for these 5 sets, so you have this gamma, and then so we well, here it calls 0 from 0. The index is from 0 to 4 instead of from 1 to 5. So if you add them up together to be 0, I think this would form this. This would form the Penrose tiling, like the Penrose tiling that we usually talk, because the Penrose tiling has different type. There's one called generalized Penrose tiling, which has the tiles that is illegal in using Penrose matching rules. That will be illegal. Okay, so after you have this grid, how do you build up this Penrose tiling?
Well, Fang, I didn't understand that last sentence where you add them to 0 and then it becomes the Penrose tiling.
No, it's not becomes if that sum up to be 0, okay, in this case, and then it will be the Penrose tiling, because Penrose tiling, you can have this many different tiles with the same type of tiles, like with the fat and the thin rhomb. You can have different tiles. Remember, there is a generalized Penrose tiling. You can have some shape like this, like 10 of them, which is like illegal for Penrose tiling, because using Penrose matching rule, you won't get anything like this. Remember? So, but here, as long as this gamma sum up to be 0, then what you get, using this dual graded method, the quasicrystal you get would be the Penrose tiling. It's not the generalized Penrose tiling, but it's a Penrose tiling that actually obeys the Penrose matching rules, which means all the vertex types would be legal.
And so when we add it up to all be 0, that means what? You've taken those distances and added them, and
yes, because they have different
pluses and minuses.
Yeah, not only is it because they're vectors. Yes.
Is this diagram accurate? The vectors coming from the origin are supposed to be perpendicular to the parallel line sets? Or?
Yes, like this one's perpendicular to this, right? And this one's perpendicular to blue. This one's perpendicular to green. And this one's perpendicular to yellow. And that one is perpendicular to red. Yes. Right. Okay, so how do we, once we have this grid, how do we generate the tile? So here, so for each intersection in a grid, and so for each intersection, we build a tile around here. So that's why it's called a dual, because the method of the dual is like, for every vertex, it's become a cell. For every cell, it become a vertex. For example, for this cell, it become a vertex. So that's the the kind of like definition of dual. So you can see here for this kind of interaction, you build a tile like that, and how you build it is this is perpendicular to that axis, to that line. This is perpendicular. That's why these two are parallel, and so this edge is perpendicular to this grid. This is perpendicular to that. So you build a tile like this. First of all, you have to kind of like forget about the size, how big this should be, but just build a tile there. And here you build a tile like that, you build a tile like that. So you can see like you can only have two types of intersections, which give you two types of the tiles. Okay, and then you would, for example, this part, if you build all the tiles, it become like something like this. So how do you build about Penrose tiling? That's why from the space of the grade to the space of the quasicrystal, it's topologically kind of like the same, but you have to shift the things around. Like basically you have to kind of shift these tiles to make them match. So if you put them together, like if you don't change the ratio or like they will not really match. Like this would not like automatically become a Penrose tiling. You have to kind of like shovel these tiles and then make them all just match with each other here. The edges touch each other.
So they all end up the same size, and they remain
Yes.
on their centers. So if their center starts on
There-
the vertex, it stays on the vertex, and you just enlarge it.
Yeah, so their neighboring relationships are the same. This must be adjacent to that one. This must be adjacent to that one. So their relationship are the same. So in a way, the topologically they're the same, but
the
like
vertex
here.
position at the center does not change. So before you enlarge it, the vertex is at the center of the shape.
You mean here?
No, just take one of the rhombs, and
Uh-huh.
that's the shape. So there's a
Yeah.
center, and the vertex
Yes.
is coincident with the center.
Mhm.
So now as I enlarge that rhomb, and I enlarge the other ones, does the
It
vertex
won't.
stay
No.
It does not. Oh,
No,
okay.
no, you have to kind of move around. Yeah,
so
their
some-
centers would not be located like this anymore. Right. Because in a grid space, you can see if I move here, you can see like all these are crowded together. So in Penrose tiling, you don't see the tiles all crowded together like this, right? And here is like a big open space. So it's more like when we go to this quasicrystal space, it's a more even. It's like a more like the density of the vertices or the density of the cells are more even. Okay, so that's the dual grid method. So everybody clear on that?
So theoretically, every quasicrystal has a dual grid construction method, even though nobody's written down very many of them. Like we have the pentagrid and we know the dodecagrid, but nobody's really done work
If
to
it is
show
a
other ones.
If it is a space-filling quasicrystal, has a finite type of unit cells, I would say so.
Right.
Yeah. Okay, so cut and project. This is a third method, which is a cut and project from a higher dimensional crystal. Okay, so quasicrystal can also be generated from cut and project a higher dimensional crystal. So cut here means select a unit layer. So in quotation mark, because I'm gonna explain what does it mean by unit layer. No, you don't want to select a really thick layer because you're gonna get a really dense space. So, and also when you select many layers in the crystal, you're kind of getting repeating patterns in a way. So unit layer of the higher dimensional crystal that is parallel to the projection space. I'll also explain what does that mean. So, and after you cut, meaning select the layer, and then you project all the point inside of the layer to the projection space, okay? So actually many of you are already really familiar with this one. So just for the one that don't know. So I realize at least, for the cut and project, there is not like just one unique way, like just there is only one way to make a cut window, for example. So for our E8 to 4-dimensional quasicrystal, right now we use the Delaunay cell, but I feel like if we use the Brownell cell, but I feel like if we use the Delaunay cell, we actually can get probably a better one for us to do this, corrugated layer. So, that's something else. We can talk about that later. So first I wanted to talk about the cut and project method using the Delaunay cell. So here we have a square grid. This is a 2-dimensional example. So it's a 2-dimensional crystal, and then we cut and project it to a 1-dimensional quasicrystal. Okay, So we start from a square grid. And then we try to, so first of all, okay, so let's talk about two-dimensional lab space, a one-dimensional tile or tiling space or physical space. So then we select a physical space. So people call it the physical space, or you can call it the projection space in some papers. So which is this space in this direction. Okay, we select in this X direction. So originally we have a big X and capital Y for the grid space. For the two-dimensional lattice, and then we select a physical plane or a projection plane that we're gonna be projecting the points on, okay? And then now we needed to cut the window. So we see the window has to be parallel to that. By parallel, we mean its boundaries would be parallel to it, like that, okay? So, but there is a thickness there. So it's not one dimension, it's two dimension, all right? So then what is the thickness? So one way we could do is we could use the Delaunay cell here. This is the Delaunay cell of the square lattice. And then we could make this like this, for example, this boundary like closed, this boundary open. Open means we don't include this point here, but we include that point there. So to make it like kind of like a one unit layer in a way. Okay, so by selecting this window, we can see, this point inside the window, this point inside the window, that point, that point, that point. So for all the points inside the window, we project them to the projection plane or physics plane, okay? And this would be the projected point. And this is which forms a one-dimensional quasicrystal, okay?
What happens to the cell's bottom right corner?
This one? This one?
Yeah.
Because this is an open boundary, so it is not included.
Okay, but what about the top left?
This one.
If it's on the boundary, I think you're saying if it's on the boundary, does it get included?
Yeah, this is get projected because it's a closed. This is a closed boundary.
Oh, okay.
Yeah, so we
It's
make
not
one side closed, the other side open. So that way, we can make it pure, like more like a unit, Okay. Because the next layer down, this will be included in the next one, but that won't.
Right.
So, yeah. Okay, so that's using the Delaunay cell, which is kind of pretty easy. And then so Sinachal uses Voronoi cell, which was how Dan used. So I took this picture from Dan. So this is a square lattice. And so what Dan did is, so first of all, he drew this, he selected a projection plane, right? A projection space, which is a one-dimensional line here. And then for all the points that has the Delaunay cell that intersect with this plane, those points would be selected. Like I said, so the window thickness would be decided by the Voronoi cells of the points. If the Voronoi cell of the points overlap with the projection space or intersect, I don't know what's the best word, the point will be selected for the cut window and will be projected to the physical space or the projection space. So like these points that is, this orange part, these are the Voronoi cell of this point. So this is the Voronoi cell of that point. So then color them that way. So you can see all these points will be selected because their Voronoi cell intersect with this line. And then after that, we select the point and we project them to this projection space. So you get this kind of point here, which forms this Fibonacci chains in this case, right? Because the angle he selected is like a arctangent 1/5. That is because the square grid has two line classes. Excuse me. So if we consider, they are made of this square grid. So there are these vertical kind of lines and the horizontal lines, or vertical edges, horizontal edges. So So once you decide a window, right? So all the vertical edges would be projected to a same length. For example, from here to here, right? So this edge will be projected to this segment. Did you see that? This edge, horizontal edge, will be projected to this segment there. Excuse me. Can you see that? Like this edge, this horizontal edge there. We didn't draw it, but you can imagine this edge that will be projected to in this one-dimensional space will project it to this length,
okay.
right?
If you think about this in terms of projecting the edges of a
Yes, because
points,
because I was trying to talk about the L and
so
S
you get the distortion
segment.
of the edges,
Yes.
right.
Yes, and so the second one is still this edge, so still projected to that as a L. So that's L, that's a L, and then so here is a vertical edge. So the vertical edge from this point to that point projected to this segment here, which is a short. Yeah, so all the vertical ones, you see, all the vertical ones project to the short segment, all the horizontal ones projected to the long.
Oh, I didn't know that.
Yeah, so I talked about this before because, depending on how many edge classes you have in the crystal lattice, you can get, like that number of lengths in the projection space. I mean, if the angle is totally irrational,
And we can do this long short pattern with the arc cosine minus 60 degree angle that we use, right?
Arc cosine in minus 6.
I emailed you and Dan about a month ago and just said, did you guys?
Oh yeah, that's the triangular lattice. That's A2 lattice, so we could get this lattice.
Right.
So by choosing that angle, we projected this as one as a L. I mean this as a L, and then this as a M, that as S, for example. So we have 3 edge classes, and they're all golden ratio to each other. So that's L, M, S. So L over M is golden ratio. M over S is golden ratio.
And so that's the Fibonacci chain, right?
Yeah, that's a Fibonacci. Well, I mean, it is one Fibonacci chain.
Yeah.
So there are. I think there are maybe like different types of Fibonacci chains. So that's one. At least it's a quasicrystal. So anyway, so everybody clear on the cut and project method? So when we do it from E8 to 240, so basically we have a 4-dimensional projection space, and then our vertical space, which we call the space that will. The space that is perpendicular to the physical space is also 4-dimensional, okay? So it's like when you project this lattice down, you have this as a 1-dimensional space, and you have another 1-dimensional space perpendicular to this in the lattice. You squeeze them, you make it disappear. So that's called a perpendicular space. So that perpendicular space for the E8 to 4D projections are also a 4-dimensional space. Just so you know.
I never thought about it until you just mentioned it, but that's a special case because the projection space is 4-dimensional,
Right.
and the physical projection space is 4-dimensional.
Yes.
Compared to a Penrose tiling, which it's not like that. The Penrose tiling goes down 3 dimensions
Yes.
with the projector, and then it goes to a 2-dimensional projector. So that's
Yeah,
interesting.
yeah, it is.
I wonder if there's a symmetry or a similarity between the 4-dimensional projection space versus the physical projection.
Yeah, I think they try to link that to the Hope vibration thing. So anyway, I think there is a D4, another D4, like 2 sets of D4 thing there. I read it before. Anyway, so let's continue. Okay, so before I go on to the third part, which are the 2 properties that which I'm gonna cover in a separate talk after this. So I wanted to kind of like briefly mention this without like a really long discussion. So this is a square lattice again. So the crystal would project it to this physical space as another crystal. You can see, right? they're equally spacing, these green ones. And then similarly, there is a purple one here that are the same thing. You can see, and it's falling off the space, but here you can keep going for a little bit. And then here you have a blue one, right? So in a way, this quasicrystal is made of finite portions of crystals, but finite though. And then not only finite, they also offset in some way.
Oh.
Hmm?
So what's going on in the middle there, where, because it's not, in the projected space in the middle, you've got your long and your short, and you've got a really, really short one between the red and the blue, or the purple and the blue.
This one?
There, yeah, what's going on there?
So we.
That means the thing in the yellow isn't a...
Yeah, it looks like the.
That might be
looks
because.
like the projection angle is wrong. Well, not wrong. It just looks like it's not Fibonacci chain because your angle is different.
Yeah, it's maybe the window that I selected or something like that, because for all the vertical ones, it's supposed to project with a short. So, but then, okay, so let me see. This is, so from here to here. Yeah, it's the window, sorry. The window that I selected is too, the window I selected is too narrow. I should have make it a little bit wider because this point is supposed to be inside. Yeah. So if I make the window, see now that we see if we make the window too narrow, then we will be getting more lens. Like these, we have 3 lenses here.
But isn't that the strength of the Voronoi cell method, in that it doesn't care about a window width, it's just if it cuts the Voronoi cell?
Right, but even Delaunay cell, you can do the same thing. But for me here, I didn't even select the Delaunay cell, because if I select the Delaunay cell, the width would be from this point to that point. You see, it should be from this point to that point. Yeah. If I use the Delaunay cell, so it's just like the width is too narrow. Like, I guess when I did this, I totally didn't ignore that part. Just select any window. But I mean, it's still a quasicrystal. It's just gonna we're just gonna skip some points. Like for example, there should be another point there. So we'll be skipping some points, and then that will end up to have more edge lengths in the quasicrystal.
For the video, can you take off the Pascal is online?
Just move your mouse a little bit. Just leave this.
And then,
mouse has to be right.
so this sum of waves, is this the idea of 2 sinusoidal waves?
Yeah, but
being
it's
offset
finite. Yes, finite of
Okay,
them.
so it's a bunch of finite sine waves being offset by the golden ratio. So, I mean, that's what it looks like, it's finite pieces.
Yeah.
So then they get broken up, and then another one starts.
Yeah, I mean, it's not like a one end, the other one started. It's like, overlapping, kind of many overlapping ones. They're not like one after another. They are, composite of them.
Like
overlap.
the green one there, those green ones are projecting down, and that looks perfectly periodic.
But this isn't a Fibonacci chain, because you can see it goes LS, 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 LS.
No, but it's fine. Dan, we just needed to open the window a little bit up. There will be other points there, but it does not affect the green one there, though.
Okay.
Yeah, there will be just more points in between.
Right, and so you can have a window of any width.
Yeah.
Okay, and so that's really interesting. So the green one's periodic, the red one's periodic, and they're really... Yeah,
you can have many periodic ones that will be all just, but they composited together, they make a quasicrystal. Yeah. So the reason that I mentioned this is to match with the number theory part. But I'm not going to talk about this here though. Okay. So this is the part for the quasicrystal basics that covered the most basic things. And the next I'm going to talk about is the empire problem. So which is one of the property for the non-locality problem. Property for quasicrystals. Okay. So the empire problem in Penrose Tiling, I think Erin already knows this part, and then I don't know if everybody else, but this is the part that I think we needed to know more because we will be using it later, or at least use this kind of concept if it's not exactly the same thing. All right, so I will cover these 6 aspects. So first is the empire problem in Penrose Tiling, and then what is this empire problem? And then I'll talk about the vertex configurations and the local empires in Penrose Tiling. And then pentagrid again, just briefly talk about because it's going to be useful for constructing the empires. An algorithm for the quasicrystal part. By the way, when we want to do a cut and project it to a quasicrystal, the angle that we choose for the projection has to be rational. So that part is very important, but I forgot to mention. So then we talk about the algorithm for empire problem and empires of the 8 vertex types in Penrose Tiling, and then the connections to our theory. It's a little bit some thought that I had. So what is the empire problem? Given an initial patch of tiles P, which is what is the empire of P, or given an initial patch of tiles P and another T, is T forced by P? So what does that mean? So we basically, in a quasicrystal, like for example, if you know this patch of the quasicrystal, can it force another tile that is somewhere else at a distance? Can it force that tile to exist? It has to be there, based on the quasicrystal rules. So this is what this subject is.
And please, everybody, if you don't understand this part, you should really speak up now, because this is crucial to everything that we're going to be doing here.
Okay.
So given that is the case, can I ask a question?
Yeah.
Previous slide. Can you explain a little bit what you mean by forced? Or perhaps draw and show an example?
Yeah, I mean, it will be more like, later it will be more clear. Because when I show the example, you would see what do I mean. Because right now, just kind of like, I know it's a little bit blurry to just use the word, but I think later on you can ask questions if you still don't understand when I give the example. All right, so let's talk about the vertex configurations in Penrose Tiling. So there are 8 types, right? So it's called the D type, Q type, K type, J, S, S3, S4, S5. So these 2 are different because you can see, in Penrose Tiling, it's Penrose built this Penrose Tiling using matching rules. So you can see they have different arrows. And indeed, I think, so one of them is called the sun, the other one is called the star. So these 2 are different, like we're going to see, because you can see these arrows are different, have different matching rules. So, okay, local empires. So the empires means, like, for example, if you, once you have this vertex type, this is one of the vertex type, which is the Q, the initial Q type, right? So once you give this Q type, and then you can see that you must have this tile here, and you must have that tile there. And then once you have these 2, and it's basically you only have one option to have the adjacent one. So all these are forced to be there based on the matching rule. You don't have any other choice. These are the only choice that you have, meaning like once you have this, and these will be forced. Okay. So is this talking about adding a forced J? So this initial Q there. Okay, yeah, so from here you add a J type here, that which is forced, and then you add these forced tiles. So eventually you will be having, you know, from this tile, from this vertex type, you're gonna be having all these tiles decided or forced. Do you understand, Amrik?
No.
Like once you have this, the only choice you have for you know, around this edge would be this. The only choice you have here is that one. So all these are like kind of forced to be there. That's based on Penrose matching rules. You know, how Penrose build his Penrose tiling is based on matching rules. And the matching rules decides, like for example, an edge like this, like a double arrow would match another tile that with a double arrow like that. It cannot have anything else.
You could put another tile there, but you'd eventually get to a point where it wouldn't tile the space
It's
anymore.
like the puzzle thing. What do we call the
Yes.
puzzles?
Yeah.
What is it called?
Tiling puzzle.
Tiling puzzles.
Oh, okay.
But it's good to understand deeply why these forces occur, and you really get that idea from Fang's slide, where she shows the cut window of the two-dimensional square lattice being projected, and you can really clearly see why there's that ordering pattern of why things fall in and out of the cut window. And so you really have that same thing happening here,
Yeah.
where the two types of decagons are the only two possible ways that
So-
the 5 cube can project to the plane.
Yeah, so these are the local rules. So when we talk about the local empires, when we talk about this global empires, and then you would understand better based on the grid method, like why some other tiles will be forced to be there. So okay, this is a patch of the Penrose tiling. You can see every this Q vertex type you always find its neighbor like that, always like that. There's no exceptions. Okay. So that means like as long as you have this tile here, a vertex type here, it will force all these other tiles to be there. So that's called the local empires. So like a locally forced tile. Yes.
That clausura relation for gamma is one of these matching rules.
The gamma?
Yes, there are clausura.
Yes. So when you sum up the gamma equal to 0, it will match with the Penrose matching rules eventually.
It's like a orthonormal frame that you have to. Each gamma is the
It's
mod of the orthonormal frame that you have to close the R4, so to close the triagonals.
tetrahedral? A pentagon, you mean? So there are 5 vectors. And then the gamma.
Some 4.
The 4? It's 5. It's 0, 1, 2, 3, 5. Yeah. Okay. Yeah.
For the
So
Penrose tiling, 5.
yeah. So anyway, so this is how they build out the local empire based on the matching rules, and then so then we can give the local empires for each of the vertex configurations. For D, it does not have an empire. That means it does not force any other tiles to be anywhere. Excuse me.
So is the white spaces in the previous slide exist because there are D configurations on the rightmost slide here, rightmost picture?
This one?
Rightmost.
This one?
Right.
That?
Yeah. So I see there are spaces, white spaces in between empires, right? Is that because
Excuse me.
Is that because you have, so exactly, so those two guys, this guy and the neighboring blue guy?
Mm-hmm.
No, those two guys, one and the next one.
This one?
Yeah. Between them there is a white space, right?
Yes.
Is that because of the D configuration?
The D configuration.
That's on your left from D.
D on
Oh yeah. This is D.
Yes.
Yeah, but it does not force any tiles around
Is
it.
that why there are gaps like that in that picture? Because there are configurations which don't force anything else?
No.
So why
Well,
Just 'cause that
the
diagram
gap
is
can be like, for example, the gap can also be this, but no, I
So
don't
why
think.
is that not forcing any of the empires?
like if you have this tile here, it just does not force anything else to be existed near it based on the matching rules. Like because I don't use Penrose matching rules, but if you really use Penrose matching rules, you can find, okay, once you start with okay, it's not this one. If you start with this, you can find like multiple different ways of build this stuff. For example, once you have this one can be flipped. So, and then here you can have either this type or that type, you know. So it's just like once you have this tile, you cannot really decide what its neighbor would be. Like it's not one option. It will have various different options. So that means you cannot force any tile to be there.
It has to have only one option.
Just one option.
To force.
Yeah, so that means you have to force it there. Okay, so then these are the local empires, you know, based on Penrose matching rules, and for that, nothing. For this is the local empire look like, and that. So S5 is this, they call it the star, right? Call it the star. And then this S, they call it the sun. So it's different. And then that's J, K, and S4. Okay? So these are the local empires, but how to build out the global empires?
Question,
Like,
what defines a local empire? Why do you have the cutoff where you have it on S4, for example? Like what,
that means
what defines that cutoff?
from here, like then you have multiple choices.
Okay.
Yeah.
So that's like a solid chunk around it, and then
Yeah.
after that you have
Yeah, once you have this, and these would be automatically existed around it, but not the tiles. Like at least
what
the
do you call
JSON.
the central object again? The central white object? What do you
Well, in the
That's a vertex configuration or vertex type.
In the people who invented the use of empire, they call that object the king or something, or the queen, and then they call the forced tiles her or his empire.
Yeah.
So is there a rule to determine the size of the empire given the king?
Yeah, using
or can it
well,
vary?
So basically, this paper it's more like a manual because it's using Penrose matching rules here for the low. It's more like a manual. You try it and you see like, oh, okay, it's up to here. It's not something that you calculate or something. You build this by hand.
You said this paper. I don't know if you heard that. Yes.
Yeah, for local empires at least.
By this paper, she's talking about Laura Dean Effinger's paper.
Yeah. So how do you build the local empires? They just use the okay. So once you have this, for example, okay. So what tile can I have here? And then you can there are different like you can have. So for this one you have a double arrow, like two double arrow, and then two single arrow. For this one you have double arrow like that, the single arrow like this. So to have something like single arrow pointing in, it seems like you can only have this tile. You cannot have any other choices. So, okay, so you must have this one. You must have this one. Must this. And after this, then for this, at this boundary, you have multiple choices. In that way, you don't have any. So the local empire would be stopped because you cannot force anything else beyond these 5 tiles.
I got that. What I was trying to get at is, okay, so if I reframe the question, do we want bigger empires or do we want smaller empires in the context of what we're going to do? Or do we even know the answer?
Well, okay, so this is just a local empire. I'm going to talk about the global empire, which is much bigger. So, yeah, so this is a local empire. So to build the global empire, so which is kind of, and then we use the pentagrid for the Penrose Tiling, okay? So it can actually find both the local and global forced tiles. So the tilings are orthogonally dual. Well, we have talked about this before. So let's skip this pentagrid method. And then here, just talk a little bit about the generalized Penrose tiling. When, for example, the gamma is not 0, which is 1/2, and then you generate from the grid method. You can have this kind of vertex types which is illegal, and this is illegal for Penrose Tiling, but this is still a Quasicrystal. It's just it's illegal for Penrose Tiling because it does not obey Penrose matching rules.
But what is this then?
This is called a generalized Penrose Tiling. Yeah.
It might be found that you cannot generate this from a cut and project.
Oh, this is generated from cut and
Oh, you
project.
can get that?
Because from a cut and project, you also have the shift vector, remember? And that shift vector is the same as this. You know, if you add up the shift vector to be 1/2, it's something. If it's 0, it's something else. So the vertex types would look different, but they're all Quasicrystals, and also they are made of 2 types of tiles. You know, one thin and one fat. As long as they have the same projection plane and then this vertical plane, the angle, the projection vector, basically. If you shift the window in some way, it will give you different tiles, but it's still the Quasicrystal made the same.
So if I take the same thickness of cut,
Excuse me.
the same. So you're saying if I take the same thickness of cut window to
Mhm.
create the Penrose tiling from the 5 cube lattice, and I have it on the same rotation relative to the projection screen, that I can generate. Well, of course, one of those 2 things has to change. Sorry, that's a false statement. What is it? The cut window thickness or the rotation of the cut window relative to the plane that creates this generalized Penrose tiling versus the classic Penrose tiling?
Okay. It is also the gamma, and then the gamma in the cut and project, you also have because it's a Z5 lattice, right? To generate the Penrose tiling, it's a Z5 lattice. So I think the center of the window also has different distances toward these different the kind of like a vectors. Yeah.
So I don't change the angle of the.
No, it's
of
not the
window,
angle.
I change the thickness.
Right.
Okay.
Yeah. But you can continue. You can still move the window, but keep the sum of the gamma equal to 1/2 or equal to 0. So be always the same type of Quasicrystal. You know, follows the same matching rules, but it still can have phason dynamics. Okay, so an algorithm for umpire problem. I even said that. Anyway, so maybe I should.
Can you explain some of the notations there? RST, what is RST?
RSK. Oh.
So yeah, so the R and S and K is the vector. The R and S is, so you have 5 vectors, you know, and then for each tile it's intersection of 2 of them. So RS is kind of like, if you label them as 0, 1, 2, 3, 0, 1, 2, 3, 4. So this vector, for example, belongs to this family 2. This belongs to 3. So you know your R would be 2 and S would be 3. Okay, so that's what RS. So each tile has this, you know, like.
What is K?
K is.
So R and S on the board is
Mhm.
a vector, but
Yes.
on the slide is not a vector. So I'm
What's
confused.
it's a number.
They
It's
tell you what grid you're on.
yeah. So it's the index.
Okay, so K is not an index.
K is not index. I think K is. Okay, let me see if I can still remember. Yeah, K is the shift
From the
vector.
origin to the
Yeah, from the origin all the way
point
to that
So the
point.
intersection of R and S?
Because there'll be
I think so. Do you remember, Aaron? Because, sorry, this is the only part I didn't look at the note again.
I'm just trying to make sense of the theorem for that. I need to understand. what
Yeah,
the
so,
theorem is.
it's the number. It's which number. Okay, so basically you have this 1, 2, 3, 4, 5. It's the number of, okay, so start from the origin, you have this, for example, in this set, you have like number 1, number 2, number 3, number 4. In the grid, you have the center, and in this line set, you have this number 1, 2, 3, 4, 5, right? So, and then something, yeah, so. I think I need a darker, yeah, here. So you have this, right? And then you have another one like this. For example, if we're talking about here, okay? And then
That is the intersection point.
Yeah.
Connects by two lines, R and S.
yeah, R and S, but also there is this number here. This is number 1, this is number 2, this is number 3, kind of thing. So I think the K.
That is R and S. Those are 1, 2, and 3.
No, this intersection is like this is, for example, number 1 plane, number 2, number 3. So it's at the number 3
like
plane.
2R, 3R, right?
Yeah. So I think the K is related to, because it's also the brown one. So it's the black 3 intersect with the brown 4. So it's 1, 2, 3, 4. So there are different things. So I think the K is kind of related to. You can see the x dot et.
So, but that K and the top K are two
Pascal.
different things. One is you have written as a vector, the other is a number.
It's the same. It's the same. Okay, so now I understand. So it's
One
a
of them is a dot product.
because the K has two
KR and KS.
yeah. So it's a KR and KS. So which make it a vector. Okay. So basically, let's assume this is a number 0 set. This is number 1 set. So this intersection would be 1, 3, and that's 0, 0, 4. Okay, so do you understand? So you have this RS as this five vectors, RS as these vectors, and you have the K as the number. You know, which number? Because this one, and there are so many intersections, so which one? So if it's this one, then it will be numbers 3 of this vector, of this set, and then the number 4th grade of this set.
Okay.
Yeah. So you need 4 numbers to index that type.
Okay, so and somehow the K has captured it in 3 ways. So RS and K instead of RS, KR, KS.
Yes, yes.
Okay, so let me then understand. So that's the tile.
Mm-hmm.
That's how the tile is tagged, is forced by a patch P if and only if max of P. What does that mean?
Okay, so I mean, I don't want it to, because it's gonna be taking so long. So we can talk about this later. But the basic concept is, okay, so imagine there is so let's use the cut and project. The grid method is the same thing, but let's use the cut and project method, right? So you have this window, and then once you select the window, you can project, for example, certain part of this in the window, the point projected to. Okay, I should give. For example, A gives this kind of vertex type. Okay, like just imagine you have this Z5, which is a high-dimensional crystal, and you select the window, and the window give you this vertex type somewhere, and then you can shift the window. You can shift the gamma, which is this, you know, in a cut and project method, the gamma is the shift vector, how you shift the window. And so you can change that so that you can still have this same vert. You can move it up a little bit, and you can move it down somewhat, like, but you always have this same thing there. Okay, just imagine that. Keep this here. When you move the window, if this start to disappear, then stop there. So if you move it the other direction and then move it until this disappear and stop there. So all these variation, you have the same tile right there.
Changes other
Yeah,
things
but
outside.
all these other things changed, but not necessarily. Some of the tiles still didn't change. When you did this variation to keep this vertex type here, there, some other tiles also always.
Other tiles outside its empire.
Don't
Yeah.
change, and that's the
Yeah,
impact.
those are there are other tiles that also didn't change during this process, and those tiles will be forced by that. Will be its empire.
Okay,
So that's the concept.
That's a new way to. I never understood that.
Yeah.
That explanation.
Yeah, so the grid method is the same thing. Like in the grid method, you can shift these, you can shift the red, you can shift the yellow, but no matter how you shift them, you can shift them around, but still keep the same tile there, and then never move that local, like that's vertex type, for example. Just never change that. But change these other as much as you can, and then you're gonna have like many so many tiles will get changed during this process, but some tiles never change. So those tiles will be forced by this vertex type. So it's kind of the same concept. Okay. So that's the algorithm that they use. That's why it's not so trivial using the computer to calculate it, because it takes a long time. And these are the result. So for the D type, there is no empire, and for the Q, this is how it look like, and this is the K. You see, this still have the local empire, and then the rest look like that. This is the J type, and this is the S. This is the sun, and this is S3, S4. This is S5, which is the star.
Can you go back and look
These are
at the
global
pictures again?
empires.
Hmm?
Yeah.
These are global.
Yeah, global empires, but they also include the local empires there.
So go back. Let's look at the one before. Anyway, so is there that other one that has is there one before that? Yeah. So this is the one that just so clearly shows how the density of forced tiles drops with distance. So if you were to draw a ring with some thickness at various radii around the center, you would find that the density per square unit of space drops with distance. That is the density of forced tiles, and that is what is so interesting physically for me, for modeling, is that an empire wave, once you make these things dynamical in 3 dimensions, will drop in density with distance. And so, Fang, this is also exciting because you just made me understand for the first time how we're probably going to derive our empires is once we understand our quasicrystal, the compound quasicrystal that is, then we'll just simply show moving the width of that shift window and just kind of compare the data set that disappears at the ends of the window, and then we can capture each empire like that.
Yeah, but it's like computationally, it's pretty like.
It'd be nice to be able to do it algebraically though, just without having to do that.
Okay.
And one more question. So does Laura Dean Effinger propose any pure algebraic sort of form of that can be generalized for the derivation of empires?
No, this is the method he used. She used the grid method, but we could use the cut and project
so really
method.
Nobody's done that yet. Like if we had that, if we knew the algebraic form of the empires in the Penrose tiling, maybe we could generalize that to think about how you define how you derive an empire without having to do all that computational handwork that she did.
brutal force.
Yeah.
Right.
Yes.
Sorry, a question on the last slide.
Okay.
So in some of these big globs
Uh-huh.
that aren't they aren't the same as this shape. There'll be other vertex types which
Mhm.
have their own empire. Say, for example, this one.
Right.
So does that mean the empire of this vertex type is a
Yeah.
subset of this
Mm-hmm,
one?
mm-hmm. Yeah, good question. Yeah, because this type, it has a very sparse, which is this one actually. So it's very sparse. Yeah. So actually includes.
Damn, that's
other-
not true, what you just said.
It is because
No, the
once
exact-
you have this vertex type, it automatically has its empire
Well,
there.
What I'm saying is Dan's exact words are, does that mean that the empire of that vertex type, the whole thing that is a subset of that first?
That's what I'm
It is.
Yeah.
It is.
The whole thing is
Yeah,
a
because-
subset?
That's what I've always said,
because
the
as
freedom isn't there.
Yeah, as long as you have this vertex type there, and it must have its empire, because once you have this one, you must have its empire with it.
Which is the full set
Yeah.
then?
Well, I didn't try to overlay because I can see that. So this is another property of a quasicrystal, which is related to phason dynamics. So here I'm gonna be talking about the Penrose Tiling Raymond dynamics. So it will be 2 talks. So I will see if I can finish them. If I can't, then we will do it tomorrow. Okay. So all right. So this is a patch of Penrose Tiling, and so we know already that we can do the cut and project from Z5 and get the Penrose Tiling, or we can use the pentagrids to get the Penrose Tiling. Okay. So then, because I'm trying to focus the phason, the phason dynamics, when I did this exploration, I was like, so is there any other way that I can look at it other than just shift the grid or shift the window? Is there anything can I find some code in the Penrose Tiling? So that was my motivation, some kind of code related to the dynamics. So what I did is, that's the thing that I did a couple years ago. I did find some on the internet, someone has a similar thing. But anyway, so I started with just following this tile and it goes through that edge and goes to this edge, so the adjacent ones. So you can see, this is the same edge class also, And then so I just follow this and follow this and then got this.
How are you following? Because you could have gone the other way.
No, because this towel, and then if you go this way, this is a.
Oh, is it halfway?
No, you could have gone right?
Yeah, I can go right. Yeah, but I have to pick one. I just pick one.
Parallel
I
lines.
start
For the
once I
parallel
start
lines,
once
parallel
I
lines.
yeah once I started with this one, then I'll go this. Basically, I'm selecting these edge classes. See, all these parallel lines. Yeah, I can go that way also. There will be another one. Yeah.
It's arbitrary choice.
How you start?
No, but each tile you're gonna be having 2.
That's the green one if you go the other way. See,
Yeah. So it will be like that one. It will be. No, but for each Amrik, you can see for each tile you're gonna be having 2 tiles. You're gonna be having someone that goes through these 2 edge and another one that goes through these 2 edge, but only 2. For every tile, you're gonna be having 2 ribbons.
So are you flipping a coin and choosing, or what?
I'm not flipping coin. You can have all of them. I'm just giving you one
Well, you're gonna show the
example.
flipping in a minute,
Yeah,
so
yeah.
you'll see
Okay,
that-
so anyway, so just follow this way, and then you got one kind of a ribbon here. I call it the ribbon. And then you can get the green one like this. You can get this silver one, this is yellow one, and then the red one. So you can get 5 of them like that. And you can get more, of course. But I'm just playing with this, start from the center tile actually. So from here I go this way, and I can go this way, I can go this way. So 5 of them. So, and they're
So you're starting from the center and choosing to go out.
yeah, I'm kind of going up that way and this way. Anyway, so and then I noticed, okay. So not only I have this one, I can also have another one that is kind of parallel to this one, right? And then another one. So it's kind of a set of parallel ribbons. If you kind of find their average, like, center line, they will be like parallel to each other. And then, okay, so if I remove the Penrose tiling, this is what it looks like. And so, like you said, I can get all the ribbons. You can see, like, all the possible ones. You worry, like, why did I do this one, why not one? Of course, you can have that one. So you can have all of them. But this is all. Like, I'm not missing it.
Flip so we can see it waving.
Well, that's little thing. Okay, so now we have all the ribbons in the Penrose tiling. This is what it looks like. And then without the Penrose tiling, you can see, like, there's this, like, 5 sets of them. This is a purple set, and then parallel to each other. And this is a blue set, parallel to each other, green set, yellow set, and red set, right? You notice that.
So it's like that's the overlay.
Can we close it for a few minutes?
Yeah.
Can you close it all the way for a few minutes? Because this is really neat. Can't get they did it all the way to the end because the light is shining from behind that. Yeah. Okay.
Right. Okay. So there are 5 sets of the ribbons here. And then you also notice there is not, because each tile is an intersection, right? So you don't see any 3 ribbons intersect with each other anywhere. Only 2 of them are intersecting. Okay, so if we take the average line here for each of the ribbon, we got this. You can see? So what is this white thing?
Pentagrid.
Is that the original?
Good. Smart. so we got the pentagrid. So what's the difference between the pentagrid and the ribbons? So in the pentagrid, I show, okay, you got the answer. You can see in the pentagrid, we have some areas like this, right? It's all like these intersection points are all crowded together here, right? But in the ribbons, you don't see any kind of like, it's all like more or less even, okay, like here. So for example, when they're too crowded here, and then the purple one, it's basically is like following this line, it wanted to go out a little bit, like away from the cluster. It wanted to kind of more or less, like don't want it to get too crowded. And so you can see the red also went out, and then green went out. And so just let the yellow and the blue intersect here, okay? So it's kind of like the ribbon is kind of the more relaxed ground state for the pentagrid. Because for the pentagrid is very rigid, and it is forced like, and then they result in something like really dense and something really sparse. But for the ribbons, they're like very even. And so now I'm gonna show a phason flip and to see how the ribbons, react with a phason flip. So this is so let's start with the green, with the blue, sorry. So, and then the ribbon will look like this going through this line. And then you can see the blue can flip to the red.
I don't know what you
That's a phason flip. You don't?
No.
Yeah, so it's that is a phason flip. You can see the blue is made, so just to focus on this area, right? So you have this tile, and this tile, and this tile, right?
That's a D.
Yeah, you have this thin rum, you have the fat rum, you have the fat rum. Ignore the red ones. So just focus on the blue.
So from this tile, you're saying instead of going to this tile, you can do what?
Yeah, so just focus on blue. The ribbons going this way because it's following this, right? Right? Okay?
Yeah.
And then the blue can flip to the red in the phason flip. And it will form the tile like this. This will be the new tile, this, and then that one.
I see.
So there's a flip.
Why the phason flip? How if a point is captured by the moving shift vector?
Yeah, so basically, using the cut and project method, if you kind of shift the window, and you're gonna get the phason flips.
It'll hop in and
Yeah,
out. And
it's
so
like
the ribbon
if we have a cube, if I have a cube, or square. Actually, I'm gonna use the square. So you have the square grid, right? And so you have this shift window like this, the cut window like this. And so first of all, like here you included that point, you're not including this point. But if you shifted that window up and or shift the window down, and this one would be not included, and then this one would include this. So this kind of flip in the Penrose tiling, like it's a 5 cube, right? So this kind of flip end up to have this kind of flip here. So this look like a cube, right? If you look at it, it's kind of like a cube. And this red and the blue are the opposing vertices. Yeah, so you can see at the beginning you included the blue one, not include the red one, but if you shift it that way and then you include the red one and the blue one would be out of the window. Yeah, so they will kind of result in this kind of phason flip.
So that's why phason quasi-particles are wave-like in this view of trying to think about how to model physics. They're these wavy particles.
So anyway, so then if we, after the flip, the ribbon would look like this. So if I play it, see, you can see the ribbon just wiggle there. That's how it look like.
Like an open string.
Yeah, it's like a little standing wave there, but nothing else changes. Yeah, so that's the overlay. And then this change also affected this pass here. You can see. So when you have the blue, right, and then you have the ribbon goes like this, and then like this. But if you have the red, it looks like this. See, if you shift it to the red, from the blue to the red, the ribbon also, see, there is shift on all the ribbons that goes through these few times. Okay, so what is so interesting about this? How can it tell us anything about the code, the phason dynamics, or the how to also the code for the Penrose tiling itself? It's kind of like a matching rule kind of thing.
What's the maximum number of ribbons that will change per flip?
An infinite number, right? If you change one, it changes an infinite number of ribbons in the Penrose tiling.
I don't think it's infinite.
If a phason flips and it's part of and it has an empire, an infinite empire, then it would change.
Yeah, but it can be the D type.
Yeah, unless it's the D type.
Just look at, because the example is actually the D type here.
Oh, yeah.
So that's why it does not cause anything else to change. Only these.
But it does change, even though the D type does not have an empire, it does cause 4 ribbons to change.
Right. But I'm gonna show you another one that is another vertex type. You can see like it's a whole infinite, flip for the ribbons.
But Amrik, in a sense, like what Fang was saying earlier, is the ribbons are in some sense analogous to the empire or the field concept around that flipping.
No,
I get that.
but here, Klee, you can see it's really like a local change. See, before and after, it's a local, and these are not changing at all because it does not have empire.
Unless that keeps propagating. So if that phason particle keeps propagating.
Yeah, but that's another flip. Yeah. So anyway, so this is, so let me go through this. I'm gonna show you an example of like infinite change. So okay, here, so each ribbon corresponds to one line in the dual grid and then to one node in graph theory. I'm trying to link this to graph theory. This is just my thought. So, I mean, anyone of you have any input, you can, we can talk about that later. So each ribbon we can think of as, here it's like a one line in the dual grid that we already know. We can think it as one node in graph theory. So then each phase corresponds to one cross point of the ribbons, or the grid also, and one edge in the graph theory. Each phase is one edge, because if the purple is a node and the blue is a node, so and then here when they intersect here, it's an edge connection between the two nodes. The lines in the dual grids are modulated into ribbons, which is the wavy lines, waved one. But this ribbon set is topologically the same as dual grid. For example, the parallel ribbons never cross each other. These ribbons are connected to the 6 clear ribbons in the 20 group.
Do they not cross each other even after the flip?
No, they don't. They never.
Really?
Mm-hmm.
Even after the flip, the ribbons never cross each other?
No. So,
If there was
But
maybe multiple flips, my guess would be the ribbon should cross. Right?
If it
Because
propagates,
no, it's just a
No,
wave.
it can propagate in any
No, it just a
direction.
wave a little bit. It does not cross. It does not cross the parallel ones.
So it doesn't wiggle as much as to touch the next
No,
parallel one.
no.
So there is a scope for the wiggle.
Right. Okay, so these ribbons are connected to the 6 clear ribbons in the 20 group and RT. So this is the RT, rhombic tricadahedron. So these kind of ribbons. So Klee used to build this model out like this. I'm just linking that.
in the 3-dimensional Penrose tiling, which is just a simple analog to this,
Yeah.
2-dimensional.
So here you definitely see the sum of the waves because of the wavy, each one you can think of as a wave, and this whole structure as the sum of the waves. So the phason flips are manifested by the waving of the waves to shift the crossing point.
Do you mean sum or do you mean sum?
Sum
SUM.
of the waves.
Some
I was
SUM.
Sum of the waves.
You
Like
sum
these,
the
you can
frequencies of
think
the
of this as a waves, and these are the waves. So the whole structure is a sum of waves.
Well,
It's a superposition
Amrik,
of the waves.
The best thing that Fang had to explain sum of waves was way earlier, where she was showing us how you can have this idea of some finite sinusoidal waves, and they're overlapped, and when you sum them, 2 or more, you can get a finite aperiodic position of 2 periodic things. Right? This was an earlier slide. That was where she introduced that sum of waves.
Yeah.
Way of explaining quasicrystal.
But here I'm really talking about this, these as the waves. Even if you think about the pentagrid, these are like think of it as them as like just plane waves, a set of plane waves, and then this is another waves, and then you basically add them up together. That will be the structure that you get. I can show you also a dynamic thing that is sum of 7 plane waves together, that it shows the quasicrystal pattern.
It's a nice video, an applet or something.
So are the ribbons the peaks of the waves? I'm
Yeah.
really confused.
Yeah.
Well, the average position of the ribbon is the peak of the wave?
The average
Like
position.
Like the straight line? Because it can't be,
Single
because it's
wave,
all
though.
like... Oh yeah, I still don't know what you mean by waves.
Each
there.
ribbon
Yeah, I
is
mean-
not a wave though.
It's not a wave, but I'm just saying. Okay, so thinking of this as a straight line, like a grade, right? And another grade that are equally
And then the
spacing.
peaks of
Yes.
a plane wave.
Yes.
So that's what I meant by the average line.
I don't
Uh-huh.
agree with that.
Why
I
not?
think it's a perturbation. There's a difference between a fluctuation or a perturbation and a wave.
Mm-hmm.
So I don't think that ribbon is a wave. I mean, it could be a sum of infinitely many waves. I don't know that. But it's not a single wave.
No, this
Yeah, no,
I'm
no.
not talking about this particular one as a wave. I'm talking about the peaks here, like like average position as waves, like a plane waves, right? So there are peaks, peak here. Okay, so for in this one-dimensional direction,
Okay, got
yeah,
it.
I agree.
Okay,
it
got it.
can be said waves, but it's like more of like a little, perturbation, like you said.
Okay, I got it. You mean the ribbons to be the wave fronts?
Right.
Yeah.
Mm-hmm. Okay, so the phason flips are manifested by the waving of the waves to shift the crossing point, like I showed before. If you wave the wave certain way, and then the crossing point is shifted, and then there's a phason flip there. So it matches with my intuition on modifying the Akasa grid. Okay, so this is another thing. Like I was wanting to modify this 3-dimensional grid, which is the Akasa grid in a wavy pattern. So okay.
Fang, that's the corrugated path on the...
No, it's different. It's like, it's instead of like straight planes, I was thinking of modify the planes and then to generate it,
How does
but I
this-
didn't do that.
How does this explain non-locality? Because whatever you told me so far suggests to me that this is a local phenomena which is propagating.
Empires are inherently non-local, except for the exception, which is the one that has no real
No, but
empire.
also each ribbon, right? So for example, I mean it's the same thing like a empire.
Ask the question. That was not the question that I was asking.
So here, for example, we have a vertex type here, and then once we have this vertex type, we have these kind of waves. I mean, I can't say like how this gonna wave. That's why I can only do the average position, which is a Penrose, which is a pentagrid. You can know there is a pentagrid here, there's a grid here, there's a grid here, and a grid there. And based on that, and then you can decide some other intersections somewhere, I think.
How does that explain non-locality?
Well, it is really like an empire kind of thing, because once you...
Okay, so let me ask my question. So you showed the phason flip thing, right?
Mhm.
And you showed that flip will wiggle the ribbon.
Mm-hmm.
That animation that you showed is a very local phenomenon.
Right, because that's the local.
Right,
that's
but
the
I'm
one-
not saying that actually talk about the non-locality. But let me show you later on, because maybe I shouldn't say it here because I haven't really showed what actually can explain non-locality.
Can you do? I'm sorry, but could you develop these ribbons around vertex changes, phason flips that are
Just wait, because I just said I'm gonna be showing other things there. Okay. So same thing. I just removed the background so you can see this structure better. And so by the way, okay, so this is the sum of the 7 waves. Basically, it's just plain waves, 7 set of them, and then the dynamics that comes from when they shift the wave.
Are those the ribbons or the grid?
Grid, straight grid.
You're saying that's the grid on the right? Well, that's the sum of the 7 waves?
Yeah, these are the 7. I don't know if this is a 7.
No, the sum of the what? Sum of the grid
That's
or
5.
the sum of the ribbons?
Some of the grid.
Okay. So
Yeah, but the grid is moving. It's like a plane waves. It's not this kind of ribbon. It's straight.
So
Just think about the straight
that's
ribbon.
like a 7 version pentagrid, but it's 7. It's a
Yes.
sextagrid, and
Yeah.
so that sextagrid is moving. It's so interesting because it looks so coherent. I mean,
Yeah.
it looks so organized. When I see a pentagrid, it looks so.
Yeah,
so
but because it makes it like a wave, like you know,
moving,
it's not like a line. It makes it like a wave, you know, like a peak
Right.
and then dip. So yeah,
You can have it also in penta with 5 waves.
yeah,
Right.
yeah,
I've got an example of that.
yeah. Okay, so so yeah, I was trying to make other attempts to decode the ribbons. So for example, when I have like, or just like kind of like when I have this ribbon, for example, and I draw a line at this, like, you know, straight line here, and I know the angle, and I calculated the angle. For example, this tile, these edges, the angle of this straight line, like this vertical line, and then these edges. So I calculated all the angles. I think this is like 18 degree. This is like a 54 degree. And that's why I was later on calling it as 1 and 3. So to explain this. But anyway, so like if you use their orientation as the type for these tiles, so there are 4 types. Okay, so this one, and this one, and this one all the same. These one are the same. So there are 4 types. And so I can code each ribbon like this. I was just hoping to see if I can find anything interesting. And so you can see a phason flip here. And now you see this kind of flip because
And this is local, do you agree?
right, this is global. This is like this whole thing gonna be flipping.
Local,
Like,
it is local. Like it's locality. The disturbance is propagating locally.
How is it propagating?
well, it's
locally?
going.
It's
It's
happening
see this is
instantaneously.
gonna be
Yeah,
going
that's
to
fine.
infinity.
That's fine, but it's still locally, right? Where is the flip at? Where is the phason flip? Show me a phason flip, the change in the particles.
Here,
No,
everywhere.
Just one. Just point out one,
Here,
right?
yeah.
that flip causes a local ribbon flip, ribbon wiggle.
I
That
don't
is local.
understand why you're
Yeah, but
saying
it's here that it's the flip here. It causes
that is it.
everything
it's
changes.
simultaneously happening.
Yeah, it's not like a
parts,
just
nothing
local.
propagating.
This is a whole
But how many
wave.
how many flips are you showing?
I'm showing this whole thing flipped. Can you see this whole thing flipped?
No, the two dots that you have. Which
See?
one did you flip?
He's asking, is there one phason flip that drives the rest of it?
I think it's the one on the top.
Or are there more? Because I can see many circles.
Well, I mean, there is an intersection point in there, but this is in my second talk. Like when you move the window in like infinite small steps, that would definitely be one point, only one point entering the window, or only one point getting out the window, and that one point causes these chains goes pretty far. So, but that's in my second talk. There is a driving. Not this one, but you can see this whole ribbon. Like no matter how long it is, it has a total flip.
But no, that's fine. But
So you can see this is flipping, right? This is flipping, this is flipping.
Yeah, but they are all local. Here in this animation, they're still all local.
Well, I'd like to
Well,
make sure
I mean,
everybody
it's an
understands-
infinite long
I'd like to
ribbon.
make sure everybody understands the two choices that we have here in deciding. Like Fang said, when you incrementally move the cut window, right, there's going to be one that pops in to the window first. But if you do it in a discretized manner, where you imagine the window moving in chunks, you know, then you get these infinite families
Well,
coming in and out.
even for this one, even for this one klee, it causes also infinite long ribbons. I'm gonna show you in the second
right, just
presentation.
spaced out. Right,
Yeah, because
we
that
haven't seen
one
that, that's
affect
what I'm
everything
saying.
else.
Okay, so we'll wait for that animation.
Yeah. So anyway, so this is just a way to just code the ribbon in this way,
Flip them back and forth a few times.
but
So what do you mean
there
if
is
you
no face on flip here.
Okay. Dugan has
So-
a question.
Yeah.
Oh, what
so
is
when
it?
you move the whole cut window for the entire global tiling, or whatever,
Mm-hmm.
why does it only do one at a time?
Well, because it's irrational. This plane is totally irrational. So if for example the boundary intersected 2 points, and so that makes it not so irrational, right? It follows a certain vector that won't be irrational. Like we are talking about like a very like some irrational like a pi, like a phi kind of irrational. Yeah, that kind of
so
angle.
Yeah, any irrational angle on like a Z lattice.
Uh-huh.
So if you move that by any arbitrary amount,
Then
Mm-hmm.
you capture an infinite number of points that get trapped, come in and out at the same time.
okay, yeah. But they'll be like scattered about.
Yeah, but it does not have to be infinite amount of time. Even one. Even if
Well,
you
no,
just
he was saying if you pick an arbitrary thickness,
oh
then you have an infinite lattice,
Right.
then there would still be
Yeah.
an infinite number.
uh-huh.
But if you were looking at a local area, then there might be some epsilon delta argument. where you
Right,
could say-
but I don't want to go
But
into
then
this.
I
But
can make it so where there's only one in the circle that I'm looking at.
yeah,
That
but I don't want to go into I won't go into this is a sentence.
Yeah,
I want
yeah.
I want all of you guys to know that we've talked about this, and if we think about, well, if physical reality is discretized and it's based on a concept just like this, then there's no reason to believe that there's a smooth propagation of the shift vector through the hyperlattice. You'd more naturally assume, well, it's discretized, so you'd have this thing changing positions in some chunks, just flash here, and so in that case, then you get these these large numbers of points coming in and out.
Okay, so I mean this last slide is just I'm just showing these edge classes. Each color shows one edge classes, meaning they're parallel, and following the edge classes you get the ribbons. And then so similar. This is a 2-dimensional. So I was planning to go 3D. So first 3D, then I would be following the parallel, the plane classes. For 3-dimensional amount tiling. Do we have a tile here? And then so the rhombohedron, you can see they have parallel faces, you know, and the fall, and just I try to go through the parallel faces by seeing here, I have a line that goes through the center of the parallel edges. So in 3D, I have a ribbon that goes through the center of the plane. Like if I have a plane like face like this, and I will have a, you know, a ribbon like this, you know, going through like that way. Can you see that? So basically also perpendicular and goes through the midpoint. So, and then
Is it different from the previous one?
this is a 3D for 3D. For 2D, see, you know, I just, these are the connected kind of like, these are one plane classes, and also, you know, they are connected with in adjacent tiles. So then I have a ribbon goes through the center point, but also parallel, you know, perpendicular to the edge class. This is the center of the face edge. So it's kind of like that.
Outside the ribbon, there are some dots outside the ribbon.
No, because the ribbon, the ribbon is supposed to look like this, but because I tried to smooth it, so that's why the dot is not
And the other
on.
illustration, she smoothed her line.
Yeah, like when I smooth this, you know, like
Okay.
because in 3D, I don't know the how to smooth it. So all the points still are on the ribbon. So I just give it certain parameters, and then they smooth it like that.
How are you smoothing it? Vaseline?
Once I have this thing, I think I use some fade or something, some
It's
curve
probably the
fade.
same as the Bessinger,
Vaseline.
Mhm. Yeah, so I didn't go, you know, very far with this. Just this will be the end of this part, the ribbon. Okay, so let's move on. And then here, when I did this part of the research, I have a question in my mind, like, if I see, how do I predict there is a phason flip? How do I know when there will be a phason flip happening here or there? So basically, I was trying to see if I can find, when I see, you know, this Penrose Tiling look like this, I know, oh, this is gonna, there's gonna be a phason flip here or there. Like why it happens, you know? Like if I know this is gonna happen, I would know like why it will happen. So, you know, like just seeing the pattern here instead of you know, thinking about the higher dimensional cut and project and all that. So I'm gonna show a phason flip here, and then like let's look at the you know, the reason there why this is happening. So you can see there is a phason flip there. Did you notice?
Is there a phason flip?
Yeah, sure.
Well, this is a driving. So focus on this area and then focus on here, right?
I can't
Oops.
see this.
Just flip it back and forth
See?
a few times.
It's flipping, right?
Mm-hmm.
See this vertex type. This is a K or
So there's
something.
only one vertex type is flipping.
Yeah.
Yes, it's flipped here. This is here, and then flipped here. So it's like a flipping here, right? So because of that flip, and this whole ribbon that is crossing this vertex type also flipped. Did you see? Like they're like a mirror flip. There is a mirror flip everywhere else except here. Here there is like a more complicated change, but everywhere else there is a mirror flip. See, before, after. If I overlay them together, this is totally like a mirror flip. And also, I notice a pattern because for these kind of a ribbon right here, it's always have this kind of towel, like a V, like a big V, small V, big V, small V, right? It's like a too thin, too fat, too thin, too fat, too fat. Also form a Fibonacci kind of a chain. So it's a long, short, long, long, short, long, short, long, long, short kind of thing. So it's almost like perfectly set up for a phason flip in a way. So so this is what I noticed.
So is this what you call non-local?
Right.
Yeah.
So it's like it's a local phason. It's a local kind of
Local
like
film
a
which has a global reach.
right,
Far away.
right. Because yeah. Okay, so the phason flipping happens only at this kind of ribbons that contains only, I said plus minus one. I think this I call this plus minus one because this is like relative to the axis there is a positive angle, negative angle, positive angle, negative angle.
It's a phase shift.
Hmm.
It's a phase shift.
Yeah, but anyway, so just forget about how I label this. It's just like, it's a ribbon that has only this kind of shapes, like always these two next to each other, these two next to each other, these two next to each other.
Can you tell me something? I'm trying to correlate this picture with the previous slides where you said the ribbons are parallel. Now all of them are going through a point. So how did that happen?
Well, I didn't draw any parallel ribbons here. These are all crossing ribbons. The parallel ones are the ones that I didn't share. For example, there is a ribbon here. If I can go back, there's a ribbon here, and then there is a ribbon like this.
No, but I thought you said the rule is to not have intersecting ribbons.
No. The rule is like a parallel ribbons never intersect.
So there is one animation you're showing for parallel ribbons is this animation that you're showing for intersecting ribbons.
Right.
And what I'm trying to understand is what is what and when and why.
So, well, but there
When
are.
are we talking about parallel ribbons and when are we talking about intersecting ribbons?
Well, there are the ribbons. There are intersecting ribbons. There are parallel ribbons, right?
To study phason flips, which ones do we want?
Well, phason flip, I mean, whatever it involves, right? So here, like these are the ribbons that are involved.
Involved in what?
Involved in the phason flip. The phason flip has nothing to do whether it's intersecting ribbons or parallel ribbons. I'm just saying, the ribbons, no matter what you like, no matter what you do with this structure, like what kind of phason flip you have, the parallel ones never cross each other. The parallel ones are always parallel. They never become cross before after
So
phason.
I got the impression that the ribbons can only be parallel.
Okay, so maybe it
No,
was-
I didn't say the ribbons can't always be parallel. I'm just saying, like, if they started with parallel, they always would be parallel. They never cross before or after phason flip.
Is it helpful to comment that this is not the empire of this? This is a subspace of the empire.
Oh, so this
If
is
you were to
not-
draw all of the things that change, it would be more than just what's in these ribbons. She's just pointing out
No, this is all.
that's the only things that change in this empire.
Yeah.
Watch the animation.
Because
Yeah,
that,
if
that
changes.
yeah. So, but the thing is, I will show you later. Because of this mirror symmetry, okay, so it seems to have a ripple there. Because of this mirror symmetry, so I actually did some work on, hand work, and I wanted to see what exactly happening between these two.
You drew that?
Yeah, I didn't draw that. I drew all these. So it's basically like before and after the flip. It's like a totally just rotating this thing, or just a mirror flip of this whole thing, of this whole structure. So you can see, like, if I just mirror flip the whole structure, this is before, this is after. If I just mirror flip the picture, they look identical.
It depends upon where the mirror is, right?
Hmm?
The mirror has to be parallel to.
Oh no, it's just spinning it round, isn't it? Like looking from the other side
Yeah.
of the screen.
Yeah. So, the center has a mirror, kind of, because the center flipped, has this kind of flip. So if you flip everything like this, and then before and after, they look identical. So, and then I also showed some phasons here, like this, And then also you can see these ribbon here also kind of have this kind of pattern, like always pairing up like that. So it's like a long, short, long, long, short, long, short, long, long, short. It itself forms like a Fibonacci chain kind of thing. But when they intersect, though, they're no longer this kind of nice looking pattern. See, it's before and after, have mirror symmetry
So
there.
the presence of the empires
Mhm.
are imposing a sense of localization of where, not localization, sorry, a sense of restriction along which wiggles or flips or wiggles of the ribbon can happen. Is that a right statement?
Can you say that again?
The presence of the empires
Mm-hmm.
are imposing a restriction on where the wiggle can happen or which direction the wiggle can happen.
The presence of the empire impose like a limit, a restriction
Along
where.
which direction?
They define it. The empire has these striations that go out, and if you flip it
Right,
back
right. I
and forth,
agree.
then
By the way.
Yes,
then-
right.
then the answer-
Uh-huh.
yeah.
Okay, so if that is the case, then is it true that, okay, so it depends on what we want to model, right?
Mm-hmm.
Why should it be the case that that the phason flip should be restricted in a manner permissible by the empires? Why not something else?
It's-
Why?
It goes
Well,
back to this
To the cut and project,
to this
right?
this 2 to 1 dimensional case.
Why do we want that? Is my question. I understand
It's,
why.
we don't
it's
have a
happening.
choice. It is well. Okay, let me answer. It is what it is by geometric first principles. We don't have a lot of choice in it if we want to use this formality. But why we would want it is that discussion that I want to have, which kind of relates to Dan's thing that he brought up and that you brought up. You guys both independently in Fang's talk brought it up, and we agreed we're going to talk about it later. Because I personally really want to dive into that because I'm thinking that we can use phason empire waves for physics, and I need help critically challenging that idea, and that is a discussion that we're going to want to have in the near future.
Mm-hmm.
Is that okay? Because that discussion kind of would include that last point that you really just brought up, which is why would we want to have that? And
Yeah. Okay. So let me just rush through this. So yeah, I mean, I just brought up the crop circle because I showed this kind of ripple there thing.
What is this?
It's like when I trace these things as just radius, and then I'm pretty sure it's gonna be also like some kind of Fibonacci sequences if we look at the the distances
Are these the
between.
shells that Aaron is looking at?
I'm not doing Penrose Tiling.
No,
I
but it's the
understand,
same thing. I
understand.
looked at the Penrose tiling and I couldn't figure out the algorithm that defines the radii of these circles. It's totally confusing looking.
Yeah.
It
It's
seems
not the
like what-
Fibonacci pattern, Fang. It's either, maybe it's a, you know what I think it is, Fang?
Well, here it does look like that. Yeah. Yeah. So and then I just thought of this, but like ignore
That's
that.
the Fibonacci pattern in that crop circle?
No.
Okay.
Okay, so let me just, for fun, just show you some Fibonacci, some Penrose tiling, like phason dynamic slice by slice. So you can see certain kind of pattern can happen in Penrose tiling when you move the cut window. So you can see that.
And then do it again even faster.
But what are you trying to show?
These are,
This is when we move the shift window, the cut window. So you can
can you
see.
play it again even faster this time? Or you can go backwards, same thing. Just kind of imagine the dynamism here. So,
It doesn't give me the sense of propagation.
right, because
It's a
because
very,
our-
very fine step, like very, very little step. Also, this is a finite portion.
So within the rules, though, you may have certain legal ordering patterns that do look more like propagating patterns.
But this is a You're sliding the cut window here.
Yeah, it's like a linear motion. Like Julio did something like more like a waving kind of
Julio, we have
waving the window. That
Yeah.
you will see more like something propagating
particle-like.
kind
so
of
we
thing.
have it in our files. Julio made it on Penrose Tiling.
Yeah, it's in
and
this
it
folder.
cop-
I didn't show. Don't have
So
time
you're
to show.
having the window which is like locally perforated, or?
Yes.
Yeah, and it made a pattern that looks more continuous looking when you play it fast.
Yeah. So we have so many of like different waves and cause different kind of phason dynamics, and with different steps also. Yeah. So yeah, this is it for the Raymond dynamics.
Not easy. And then it continues for the next talk, right?
This
That's what the other
this
one-
is something else. This is not that.
Can you